ESR, so they can have an idea basically of what we are doing and how the research they are doing is going to be applied. I'm not going to be talking specifically about polynomial optimization, but more about optimization, I'd say, in general, and what it could, let's say, yield as results and what we can produce with optimization techniques for clients. So we'll be discussing some examples, some applications, and what's the job, let's say, as an optimization practitioner in industry. Feel free to interrupt me and ask me questions anytime. Feel free also to let me know when I'm reaching the timeline, as the presentation is probably longer than an hour, but I have, let's say, skippable parts that I will not be presenting. So to start, I would like to say a few words, let's say, about Artelys. Who are we? So I'm working for a company named Artelys, which is a French SME. I've joined them after my PhD thesis a few years ago, let's say. So Artelys is a small French company, well, medium now. We're around 80 to 90 people. All of them actually have hold a master's degree, and for a large part as well a PhD. So we are, let's say, we have an engineering culture very strong, as well as a research culture in the company. And our goal as a company is to bring some state-of-the-art technique to the client, to our clients, and to be able also to innovate and bring innovations to lots of domains. And we have, let's say, a strong specialization in energy, both for historical reasons, as our founder come from EDF, and also because, as you'll see, energy is a domain where well, there's a lot of things to do, let's say, with optimization. So we are, let's say, building solutions as well as providing studies and so on. I'll say a few words about that quickly. So basically, the services that we provide are manifold. So we provide consulting services, especially through studies, which most of the time, for the very large part, actually use quantitative techniques and quantitative mathematics based on optimization, but also data science, statistics, machine learning. Everything basically that has maths in there is something that we practice, I'd say. And we are also building software. And when I'm talking about software, there are multiple types, I'd say, of software. There are the numerical cores, the solvers that we are building, but there are also everything that's around, and that's also very, very important. As you are discussing with the client, you can just expect them to run command line scripts and be happy with that. So you need to bring something else to the table. So first, by helping, let's say, people with modeling. So the modeling tools as well are very important, but also the visualization tools are quite important, and that's why we built this Artelys Crystal Suite, which is basically a software suite which revolves around optimization, and whose main idea, let's say, is to make it easy to connect to optimizers and to visualize results in many different ways, and in order to be able really to understand them and to carry the knowledge from one person, let's say, to another. We are also building customized software for the clients, and that's mostly what I'll be talking about today, customized software and for optimization tools, which is a very small part actually of our activities. So I just mentioned optimization tools. I won't go into details, but just so you know, we have a partnership with FICO, and we commercialize FICO Express. We are heavy users as well as of FICO Express, and quite happy about it, I must say. Internally in the company, we develop also two numerical optimization solvers. One of them is Artelys Nitro. So this is a general purpose solver for nonlinear programming. including black box programming and mixed integer nonlinear programming, and Artelys Calis, which addresses constraint programming problems. So I mentioned earlier the Artelys Crystal Suite. So just so you know, we are making a few software, I call out-of-the-box software based on this suite. So typically, so you have an idea what we are doing with it. One of them is Artelys Crystal Supergrid, which we use to analyze pan-European capacity expansion planning and network. So typically, the European Commission has bought the software and is using it directly, also through the Joint Research Center and through a study to analyze the impact of policies, typically, of energy policies over the power systems in Europe. Then we have Energy Planner, for instance, which is dedicated to operational optimization. So how do you plan for optimization for gas turbine, for instance, or for a specific power plant? And we have other softwares like CT, which is devoted to analyzing the impact of policies at the local scale, or NextGrid, which is more about understanding how things happen on distribution networks. You'll get an idea of what this is right after, and doing some simulation and design optimization, especially with respect to the integration of electric vehicles. And we are not doing just energy, especially we have another software which is based on this suite, which is Resource Optimizer, and which is dedicated to, as you guess, resource and activity planning. So that's just now, I hope you have an idea about what we are doing, and I want to come back about one point specifically, it's R&D, especially for a company like ours, it's very important. As I was discussing actually yesterday with Andreas. So we roughly spend 35% of our time doing R&D projects. So it's not just R, there's also the D in there, but it's very important because for a company like us, you need to be at the state of the art, otherwise you're quickly irrelevant, basically. And so that's very important that we keep investing in R&D, develop our solutions and develop new solutions as well with cutting edge techniques and advanced science as well, especially as we are doing with our solvers. So that being said, so I skip through the client. I'll introduce a few notions about power systems, which basically with the talks from John, Miguel, and others, you should know by now, but just so you get an idea how this is roughly working. And then I'll be discussing a few applications. So basically, the word here, which is important, is simplified in the title. So basically, how does the power system work? So you have a generation someplace, and you have a consumption someplace else. In between, you have to transmit, of course, the energy and so deliver it. And for that, you have networks. And especially, you have two layers of networks. You have what is called the transmission network, and then the distribution network. And the idea, so, is that you generate the energy, so it is being consumed. But something is very important on power systems is you just, for instance, you just can't produce more so that it's fine, you know, you have enough to cover the demand. That's not how this works, because if you do that, you have other kinds of problems. And so the difficulty here is that you have to make sure that the production and the demand are equal at all times. So that makes it very difficult actually to plan things and to run them and make sure that the system is going to work, especially if you have some outages and things like that. And that's why typically I think Miguel has discussed some applications about OPF, and that's why this is very important to be able to simulate the network, especially in case of outage and so on. So just a small picture to illustrate that. So basically the transmission network is on top here in the picture. Here you have the large power plants, like gas, nuclear power plant, the big hydroelectric plant, and so on. the transmission network, so the big lines that you can see next to the highway, next to the in the fields, and then you arrive to the cities, villages, and then that's the distribution networks that carry the energy from the input point, let's say, of the transmission network to the final client. Of course, it's not just as simple, so that's very simplified here, but as you guess, if you have some solar panel on top of your house, then you also have to inject your energy back into the network, and you have also some bigger producers or bigger consumers that are directly plugged to the transmission network and so on and so forth. So I won't go into the details, but basically you get the picture. So now that this is understood, let's say for everyone, we'll be able to discuss a few things. But first, I want to give you some ideas why it's interesting for us as optimization practitioners to look at the energy market, I'd say. So first thing is, this is a very large market. So it's hundreds of billion euros market actually. So there's a lot of money, lots of stakes in there, and optimizations have a lot of things to bring. There are many actors, from small to very, very large companies, and there are many costs that come from very different things. Obviously, there's the investments when you have to build a power plant, when you have to build new lines, that's costing hundreds of millions of euros. Then there's the operations. So when you produce, for instance, some energy from gas, well, you need to buy the fuel, you need to decide how you are going to produce, in which market you sell, and so on. So there are also all of these operations aspects. There's the longer term as well, the policy making. So you may feel that a policymaker just flip a coin and make decision. That may have happened at some point, but in energy, actually, the decisions are very informed. There are lots of reports that are produced, lots of studies that are made actually to compute impact assessments typically of policy decision and to help our policymaker to make the best possible and well-informed decision. And of course, there are all of the stakes that are related to energy transition. So there's lots of things to think about, very complex problems. So Jean has discussed a bit about dynamic simulation. Miguel has discussed about optimal power flows. Typically, there are also long-term simulations. And of course, all of that, it's stochastic because, well, you never know what happens until it happens. So you have to take into account that you don't have perfect information, and there's really an inherently stochastic aspect to power system. So here are typically the optimization problems that are related to these different aspects. So it's related, as I said, to design, portfolio management, auction clearing as well, which we will discuss today, impact assessment, trajectory, capacity expansion planning, and risk management and financial risk management as well. And as an optimizer, actually, and a scientist, why would you look into that? So, as I said, this is a domain where, let's say, you can have actually a high impact, both financially, but also in terms of security, whether it is human security, security of supply, or system security. In terms as well of policy making, as I said, when you make a report, that's going to be read often by lots of people, including policymakers, so you really have an impact there. And there's a lot of room as well for scientific and technical innovations. There are things today that we still don't know how to do, like dynamic simulation, for instance. It's a very, very challenging topic. At the very small scale, you know how to do a few things, but at larger scale, that's terribly complicated. And even not going into that, optimal power flow, you have challenges related to stochasticity to solve thousands or hundreds of thousands of them, or simulating very large networks with unit commitments and so on and so forth. And basically, all optimization techniques that you know or you may know are applied one way or another to solve these problems, and every innovation is basically welcome. So that being said, maybe I'll take a question or two if there are at this point, and then I'll discuss some examples as mentioned previously. Is there any question in the room? Yes? Yeah, I think it's better for everyone to.
You also like develop dashboards for like real-time monitoring of the system, of the network health and such.
Yeah, that's also things we do actually. So RT, for instance, has lots of such dashboard, and now we are working with them to do such dashboard and also to relate it to some computations. But mostly we are doing it with our clients, typically that operate power plants. So, for instance, you have the optimization that runs that say, okay, that's going to be the plan. That's how you are going to operate the power plant. And then you have the dashboard, which is seen by the operator, which basically turns the button to make sure that the turbine is working as it is expected to be working. And if something happens, that happens a lot actually, then there's all of the cycle that makes it visible through the dashboard, and also that you can automatically re-optimize and provide a new plan and have all the validation aspects and things like that, because you don't want to have a new production plan going into operation typically without someone validating it. Okay. Anything else? Or I move on to the application. Okay, I don't hear anybody, so I'm going to speak about the first application, which is a long-term study, and I think a very interesting one, because that's, so I'm going to give a spoiler actually. That's a place where you'll see that we can put a lot of mathematical, let's say, things in place, do lots of things in the end to produce very few but very important results. So typically, that's a study that was done a few years ago, actually, quite a number of years. That was in 2015 for the French regulator, that called Commission de Régulation de l'Énergie, with partners which were Adéquation, who are economists, and Thomas Olivier Léautier from Toulouse University, which was doing the state of the art. So basically, the study was named Tarification des injections sur les réseaux de transport. So in English, injection tariffs on transport and distribution networks. So that's a big question, actually. And that's the first thing you need to understand when you're doing a study. It's basically, what's the question? So originally, the question was this. Should we introduce an injection tariff for electricity generation? So it means that if you are producing 1 megawatt hour and injecting it on the network, you pay something for the service that is related to carrying this energy to the final client. So in France, only the final client currently pays for that energy-related cost. So, but, well, that's a big question here. What are you going to do with that? Well, basically, the first thing you need to do is to make it as, I'd say, an actual question. Actually understand what's the real question that's behind it, what you really want to study. And in this case, the question was whether a geographical distinction between generators would make sense. So, because in introducing an injection tariff for it to be the same for everyone across the country, it's just useless. Basically, it's just putting the tariff some places, but in the end, it's going to be paid by the consumer. It makes sense if it differs from one generator to another, and especially to the main, and probably the only one criteria that makes sense is to have a geographical difference in between generators. And the second question, if you introduce such a tariff, it it must have a purpose. So what's the purpose? Actually, the purpose is to provide long-term signals to generator, to tell them, okay, you're missing energy in this area, so go build a power plant there because it's very useful for everyone and it's going to spare some network costs. So you need to have some signals that are stable enough and that really provide medium to long-term information. So you don't want that someone now builds a power plant at this point and that changes everything and he doesn't benefit from this injection tariff typically. So that's basically the idea and the questions that were behind this study. And of course, then we have to understand what we need to do to answer that question. So basically, the idea was that we would compute the regional transportation cost disparities. So we are not interested into the whole transportation cost. What's interesting is that how different it is to carry 1 megawatt-hour of energy in Brittany, for instance, compared to Central Region. That's what matters. And the second aspect is the robustness and the stability of the signal that would be obtained. So quickly going into the details, I skip through most of that, but so you get an idea what we've been doing. So in terms of modeling, actually, we've modeled the French electrical network based on historical data as a regional model, flow model, and we've used historical data to reveal the let's say, historical flow. And in terms of mathematical approach, basically it's not super complicated. It's a QP model that was modeled in Ample and solved with FICO Express and Nitro. You'll get after why we use Nitro as well. And of course, when you're doing such a study, there's a lot of discussion to have with the client. First, because you need to understand what's solved by the client. What's the real question? In order for them to have a real use of the results, what do you need to do? That's never obvious for the client, and that's also hardly obvious for you as you work on the project. So you need to really carry out, let's say, that what you are doing and explain it so that people can make sense of it, understand it, and in the end, you need to somehow educate them so that they can adhere to what you propose and they feel like it's the good thing that answers their question. And most importantly, they can also defend those results, because in the end, they are the ones exposed to the stakeholders, not you. They will be defending the results to various types of stakeholders, so they have to feel kind of safe explaining them and understanding them well enough. Preferably without understanding every single equation of the mathematical model, because that's not their job. So in terms of model, the idea was basically it was a minimum cost flow problem. So that was a quadratic problem. The one we've solved, not the actual one, you'll see why in a second. And the input were the production and consumption historical on the network at an hourly time step. So it means 8,760 time step over a year. Loss factors and interconnection costs between regions, because we were building an adaptive network. Go into the detail, but when you do that it's usually a good idea to do things on the network that would be best rather than on the actual network. And also some costs that are related to loss of load, which is the cost of the energy you do not provide. And the output of the optimization box was an adaptive network, flows, and dual variables. Most importantly, the primal variables, I'm not so interested in them, but the dual variables, they are very important. First thing, as a practitioner, you need to understand is, well, the input, usually it's unusable, the data you get, even when it's been treated before, when there's been some treatment and so on, and the data is supposed to be solid. Well, it's never the case. So there's always a huge work to do on the data to rebuild something that's completely consistent, and also to reconcile the sources, because usually you use more than one source, and the data is not exactly consistent in between a source and another. So I wanted first to emphasize this point, because that's something you can just not forget or skip. That's very, very important. As I said, when you're doing an optimization, you can have the best bugs in between, but well, if you have cheats in, then you get cheat out. So you must have strong inputs in order to build something that's really relevant. So basically, in terms of modeling, that was a simplified modeling, regional modeling, as you see here, with exchanges between nodes and a single construction and production nodes, node per region. So there's lots of things to do, but I'll skip that, as that's not the main subject today. For the model, basically what you need to understand, also won't go into all of the details, is that in the formula, so we're talking polynomial today, you have a polynomial here. Tau is between 0 and line, and 1 is the usage rate of the line, and C is the capacity of the line. Both of those variables are optimized. So earlier on, I'd say it was a quadratic model. Obviously, this is not quadratic. So you need to do something to solve that problem and be relevant. So the idea, basically, it's something very, very simple. So it's basically to do an order 0 approximation and to have an iterative scheme to compute the capacity. So the tau, I told you, it's basically the flow over the capacity of the line. So what you're doing basically is that at each step, you optimize the capacity and the flow, but you assume that the capacity is the same as previous iteration. We could have some discussion about convergence of the scheme, but I'll also skip that for today. But what's important to remind is now that we have a convex QP, so it's something that's rather nice to optimize, I'd say, and we can solve it actually using a sequential algorithm. So basically, the algorithm is to solve the QP, so update the capacity, restart until convergence. And what I didn't mention is also the reason why you have nitro in the end. As you get a point in the end, that's very good. Then you also want to have a local optima, having into those cubic parts taken into account on the objective. So you take this last solution and you redo one optimization to obtain a local optima, actually, as you have a very good starting point that's not so difficult, even if the problem is very large. Keep in mind that this problem is solved on almost 9,000 time steps, and every time step is coupled by the capacity of the line. So now that I've told you that, why am I doing that? What's the use, basically? The use actually is to get the dual variables, because the transmission cost disparities between the region, it's actually the difference between the dual variables of the flow conservation constraint. And so now that I have those variables, I can do things. I can especially display results in this way, for instance. So typically we've evaluated, for instance, that there are cost difference up to 5 euros per megawatt hour. So basically the energy, well, not these days, but usually it costs around 50 euros per megawatt hour. These days there are other questions that may see that it can reach 400 or even 1,000 euros, and that's normal. But at this time, actually, it was more about 45 euro per megawatt hour. So 5 euro just on transportation cost, that's a lot of money, actually. So that's the difference between let's say, transporting electricity from the far somehow region to the closer. And here you have a map. And actually, if you work in energy, you can really relate to this map for a few very good reasons. So first, you have Brittany in red here. Why is that? It's because you have simply very little production in Brittany. On the contrary, you have a lot in center region and rural. So there usually it's cheaper, let's say, to bring electricity locally. And you have another red region, which is here the southeast of France. And here there's a geographical reason, especially if you want to bring the electricity typically here next to Italy, you have to do something like that. So you can't just go directly to the region, you have to cross the mountains. And so that's actually more networks. And there's not as much electricity generation either, so that explains the cost difference. So that gives you a first idea actually about the results you obtain, and then you, let's say, increase the number of scenarios, make it so that you can study typically the robustness of the signal that I mentioned. So typically what we've done here is we've generated additional demands using statistical model, and we've computed the generation based on a market model actually of France with all the generation per region. And so we've optimized actually the production plan on a rolling horizon. So we can get the corresponding generation. And we've used that data to then reintroduce it into this box and compute what will be the resulting map with basically some assumption on the transmission capacities. And what you obtain basically in the end is such a set of maps that tells you both on all of these scenarios what's the cost disparities, and also more importantly, the second result we were looking for is what's the, well, how much does it change from a year to another, because you don't want to have a tariff typically which is very different if you have a hot year or a cold year actually, or wet and dry and so on. So typically you have on the years we've taken, you have all of those different sets. I'd say they are quite representative, and what we can see is that the graphs are very consistent. Of course there are changes, but it's very little compared to the order of magnitude of the cost disparities. The order of the difference is roughly 10 cents per megawatt hour. So it proves actually that the method is quite reliable and the costs are quite stable. So in the end, what we've done is we've deployed complex numerical methods. We've treated very large volume of data. You might not see that through that explanation, but that is the case. There are lots of data processing, lots of tuning, lots of work on the optimization. There was quite a big technical report, including also all of the mathematical details, so they can be audited and criticized if necessary. And so we've done all that to produce basically just this drawing, this 8 map. So quite some nights, quite some months of work just basically to produce that, because nobody cares about the rest. All they want to see is those maps. And here I'm going to give you my personal opinion. So I think that actually this is quite a success. This is quite a success because we've been doing some very complicated stuff, and we've been able to provide the response to the question the client had in the simplest possible way. That's very exploitable, and that's something you can present to policymakers, for instance, and they can relate to and they can understand. So really making your results accessible is something that is very important as a scientist and as an optimization scientist, to make things so that people can relate to your work, understand it, and actually make use of what you've done. I have no idea where we are with respect to the time. You tell me, Bernard?
20 minutes.
Il nous reste 20 minutes?
Yeah.
Right. Okay. Very good. So I'll discuss now a second and last example, and I skip through the last one so you can ask some questions. So I gave you a first example of a study, and now I will give you an example of something else. So here it's really an optimization code or trans-European replacement reserves. So there are some teaching material as well to go through here. I go through them very quickly, as I assume you know quite a few things already about them. But most importantly, there are two things you need to know. One is that, as I said, you have to equate the production and the consumption on an electricity network. And obviously, there is no perfect forecast. So nobody knows what's going to be the consumption, even of this building in 10 minutes from now. So there's no such oracle, that's impossible. So what you need to do basically is to permanently adjust the generation to the demand, and also adjust the demand to some level. And to do that, financially, you have some markets actually that are organized from the very long term, so a few years in advance, to the very short term, a few seconds before activation. So typically, let's say I'm EDF, what I'm doing is as a supplier to final clients, not as an energy producer, I will be buying some electricity, but mostly from myself, long term in advance, because I know typically what's the base load actually that I need at least this amount of money, so of electricity, so I will secure some amount on the long-term market. And then as you get closer to real time, you make some more deals on the long-term market, and then you have a gate which is called the day ahead. So you have some good forecasts now, let's say good enough, of what is going to be the generation and the consumption, most importantly tomorrow. So you can adjust on the day ahead market, and then keep on exchanging energy on the intraday market. And then you get there's a sort of gate, which is you get to real time. So you're 1 hour before the supply of energy, in this case of electricity. And so now it's not your business anymore. Now it's called balancing, and it's the business of the transmission system operators. And in France, that's RT, for instance, and Jean has discussed that a bit already on Monday. And so as you get to balancing, the matter is not just economically matching supply and demand, but it's also the security of system. You must ensure that the system will be safe, whatever happens, especially if you have an unexpected peak of demand or an unplanned outage, most importantly. And of course, you must be able to fix the gaps in between the supply and the demand that could not be accounted for, because it's just, as I said, impossible to have perfect forecasts. So we'll be discussing today balancing markets a bit, especially one of them. So in terms of balancing markets, you have multiple of them. Those are called the reserves. So you have the primary reserve, the secondary reserve, and the tertiary reserve. And we are just going to talk today about the replacement reserve here, the ARA, which is basically a tertiary reserve, which is used to do some more activations after secondary reserve and replenish the secondary reserves as well. And the very last thing I need to tell you about is its market clearing. So it's a simple economic notion. You've probably all seen a graph like that when an economist explains you what's a price. So that's, as you know, the intersection between supply and demand. What I want to see here with with you today, it's not just the price, which is this black dot as well, but this pink surface here, it's what's called the social welfare. So it's the total money, let's say, that is made or spared thanks to the existence of the market. And you can decompose that into the consumer surplus, the producer surplus, and the congestion rent as well, which is not on this graph, but let's just keep in mind the social welfare. So yeah, just a few things about social welfare. Left as an exercise. So if you want to do a drawing and see one thing that's interesting is that social welfare does not depend on the market clearing price. So if I move the black dot here, it doesn't change the social welfare. So I leave it to you as an exercise to see why this is the case. Good. That's a simple problem. Why are we involved at all, actually? Just have to draw the curves and see where is the intersection. Seems simple enough. But of course, things are not just as simple. And especially when you relate to energy markets, you want to have things like complex projects, because it's false typically to say that a turbine can produce just 1 megawatt-hour of energy. There's a technical minimum. It cannot produce less than 10 megawatt-hours, for instance. So you need to have some products, what's called complex products, which typically are blocks or products with minimum quantities, or other products like exclusive bits and so on and so forth. Also, in term market, especially, you have multiple time steps. So you have time steps that are linked in time, and when you're doing the clearing, you're doing it for 4 quarter hours and not just for one time step. And of course, you can link your generation, because typically if you produce for the next 15 minutes, well, possibly you can't get to zero right after. So you need to have some relation in between what you're doing now and what you'll be doing in the next quarter hour. You have also some network constraints, and especially in relation with market cooking. So inter, we are looking at Europe. Actually, I have a map after, you see the region. But what's important is we have like Italy, France, Switzerland, Spain, and so on. And all of those regions, and therefore their offers and their price, are coupled through interconnectors. And of course, you have some complex rules of price that makes it that not any price is acceptable, even if it seems to make sense. So you need to have some strong post-processing, let's say, on price. And well, if you are planning to use some dual values, you're gonna have a hard time doing some stuff, which I will not be discussing the rest. But now, just you take that simple problem, you add all of that stuff. Well, basically, what remains is a very complex, actually, optimization problem, and a complex optimization problem that you have to solve in operation, in real time. And that's the whole thing about this project, and that makes it very difficult. So you started from a 2x2 Rubik's Cube, and you end up with that. And you still have to do something, so I will be telling you what we are doing, basically. So you have the region right here. Currently, it's live. The algorithm is live on those blue, dark blue regions. So France, Italy, Switzerland, Spain, and Portugal, and Czech Republic as well. And it's soon to be live in the other regions that you can see here. So basically, the project was to implement the market clearing algorithm and to abide, of course, by some complex specification, which includes typically a robust and high availability solution. So that's the kind of solution that has to work even if a data center is burning. That's the kind of high availability you require, and that's also that has to return solution within a very, very limited time frame. So in this case, it's let's say contractually 3 minutes, but I think it's running in 90 seconds maximum in operation, and it has to deal with up to 500,000 bits. So that's very large volumes of data. You have to compute, of course, the best possible solution. I'm not saying optimal, because optimal would be great, but at some point you have to be reasonable. So that's one point where you are reasonable. You're just looking for the best possible, which is a bit better than good enough, let's say, and in very limited time. And you have also to integrate this computation engine within a very complex software architecture, because that's, even if it's central, it's just a small building block in the whole scheme. So you have to keep in mind that you're going to be integrated with a dozen of TSOs, and that's a complex operation. And the algorithm itself has to abide by some complex business rules, including also some that are, let's say, not well formulated, especially regulatory constraints. So if you've done the exercise once in a life to read a law and find out how you can model it, well, that's a very funny exercise, let's say. Could be quite a gap in between how lawyers write things and how you're used to do it, actually. So just a words about how do we actually implement this solution. So typically, the objective is to maximize the social welfare, so that pink area earlier, if you remember. So in other words, roughly, it is to satisfy the needs at the least cost, actually. And you also have to compute zonal prices and abide to the business rules, while at the same time you have plenty of problems like the price rules I mentioned, and many indeterminacies. So basically, the algorithm in the end, it looks like that. So you have a main optimization problem that you see right here, which is basically a big mixed integer optimization problem, mixed integer linear optimization problem. And this problem will compute solutions, and every time you get a feasible solution, you start what we call a finalization problem. That is what you see right here. So for those who are remote, I was pointing first this top area, and I was first pointing this part, and then this one, which is basically every time you get a solution, you make it so that this solution to the first problem is actually something that's cleaned, that has valid prices and so on, and that you can return within the time, because in the end you don't know how many solutions you will be able to finalize and return within the dedicated time. And there's also a very important component which is not to be forgotten. It's the software. So the algorithmic approach it's one thing. It's one that I think everyone in the room can understand. But when you're doing such a solution, the software also matters just as much, if not more, actually. You have to make something that's super reliable. And so you have to do lots of software engineering. And here are just a few ingredients, basically, of the problem. So typically, microservices, redundancies, you need to rely on strong and reliable solvers, good modeling language, and so on. So typically, you have the technologies and the main ideas here that we use. And you can imagine that the amount of time that's devoted to the software on such a project is at least equal, if not much, much higher than the time devoted to doing the actual optimization solution. Of course, I didn't discuss with respect to the optimization solution, but there's also a lot of tuning, about a lot of learning, and improving things across the time and tests. So maybe just to finish with that, the solution is live since January 2020 in the regions that are mentioned here. Typically, it's used so to make sure that replacement reserve is provided to more than 200 million European people. I would say citizens, just so you know, there's Switzerland also. And there's been already more than 15,000, maybe even 20,000 now these days, auctions that have been realized. All of them were successful, so there was 0 incident. And the volume that it corresponds to is typically 500 gigawatt hour to 1 terawatt hour of balancing energy exchanged per month. So you can do the math if you want to see the money involved typically, but that's a lot. Okay. If you're curious, here are a few information, and if you are very curious, there are a public presentation of the algorithm with much more details that's available on the ENSOE website, and there's a YouTube video that you see right now. So I've said a lot already. I skip through that last part just to discuss the small conclusion, and we'll finish with questions. So just basically the message I wanted to provide you in the presentation today. So it's, well, there's a lot of things to do thanks to your skills, the one you acquire in your PhD and the one you've acquired before, and the ones also which are yet to acquire. And going from academia to industry, there's a lot of things that you're gonna be able to use directly. But what you should keep in mind if you want to be, I'd say, a fine practitioner, what you need to be is a good scientist, know a large panel of techniques. That should be, let's say, no dogma, no religion. You can't just know one thing and stick to it. You have to know lots of things, not in all of the details, but at least know there exist, know there are advantages and drawbacks, so you can pick the right approach for the problem you're working on. And you should have an idea as well how to implement them. So that makes you a fine practitioner. Let's say you can start now working, but the question is what you need to be actually to be a great practitioner. And here I will relate actually to some things that Jan said on Monday. So obviously to be a great practitioner, you need to be fine, but also you need to have a few more things, capabilities, let's say. First is to know how to validate what you are doing. So from both a methodological point of view and from the code standpoint as well. So that comes with tests, but that includes both, I'd say, unit tests, but also functional tests. And as I said, you need to validate as well the methodology, which is more high level. You need to be a good ear. You need to talk to your clients. You need to be able to translate a business problem into a model and to iterate, because, well, you might get it right on the first time, but that's not happening very often. Usually you have to iterate quite a few times with the client to really get to the bottom of their problems and solve them. And you need to be critical and constructive. You need to be able to weigh the benefits of the different approach and also their costs and their related risks. Often you can be tempted by some state-of-the-art approach to solve one problem, but you need to understand whether that's reliable enough to, for instance, like we did on there, to provide a solution for every auction that is going to happen for decades, actually. So it needs to be that reliable. Some others, it doesn't need to be. It's just something you're computing once. Similarly, as I've shown in the study, and there, well, it's okay if it crashes sometime, as long as you know that the results are correct. So you really need to rate the benefits and the costs and risks of the different approach to select the appropriate one and pick the good solution for your problem. And of course, take a step back on what you are doing and be open to critics. Thank you very much. I think I've passed the hour, but I'll take questions.
Thank you very much, Michaël. Any questions from the audience which is present in the room? And if so, could you then please come just to a microphone? I don't see anyone raising a hand.
Maybe.
Oh, yes. Please, it's just a small screen, so just come forward.
So in this development that you software that you do, so do you have the need to certify? So the certification of the results which
so
happen in some places.
Not in the sense that you're thinking, I think. So we don't need to have like a calc or mathematical proof of the programs we are doing. That could happen in the future, or doing some GMP computations or things like that. But what you need to do typically is when you what you are doing should be auditable. So someone else should be able to review it and validate what you are doing. And when something you provide is actually a solution, so usually actually on client side there's a checker. So there's something that will check the solution and verify that it's actually what it pretends to be. So when typically it's the output is a production plan, and you say, okay, that's this production plan, and the cost is 700,000 euro. There will be a checker on client side that will check this production plan, verifying that it's valid and that the cost is indeed 700,000 euro. But it's, I'd say, practical proof based on feasible solutions that you return and then evaluation rather than mathematical or computational proof with very high precision. There was another question. Does that answer your question, Dana?
Yes.
Yes.
Just wondering, you gave the example of the energy markets, and you said you also developed like a suite of 5 different softwares for essentially you have big complex systems and you need to kind of manage it to optimize it. So I'm just wondering, stuff like water distribution, internet, and do they all also come with their own really complex system of things to balance and optimize? And this might be a bit out of the reach of Artelys, but
so actually, we've worked in the past about water distribution. We have some problems typically, which sure that's the word, but which valve you are going to open and close to have the network operate at the desired flow, and also to be able to perform some maintenance operations. So there are some problems that happen in network distribution. Those are quite different than the one we are discussing because it's not a bad approximation when you have a line to say that the electricity that you replace needs to be at the same time. Let's say in water and also in gas networks when you have pipelines. Since gas it circulates at something like 30 kilometers per hour. It's not very fast. So you can't just ignore things like the line pipes and things like that, and it's not linear relationships as well. So those are different problems, but you have some optimization problems there as well.
so you say there's a lot of transferable skills in this from these problems to the next, even though the problems themselves.
The transferable skill, in my opinion, are not the skill that relates to the specific problem, but they are your skill as an optimization practitioner. Because, as I said, we need to have some large portfolios of techniques, but preferably still with the basics. But if that's the case, if you know how to do optimization, mixed integer optimization, and non-linear optimization, then you can apply those to solve, to model and solve problems of power networks, and then to move on to water distribution network if you wish. But in between, you'll have to learn the business aspects, which is, let's say, not hard to be, as long as you have the client that's alongside you and that understands that you are experts in your field, and he needs to bring his knowledge on the table, which is also very valuable for him, and to explain a few things to you.
Thank you.
Welcome.
Anyone else in the room?
Yes, then you want yes, so you mentioned this optimization, balance market optimization example, and then you choose the FICO Express solver for that. Can you explain a little bit more what was the rationale behind this solver, and because you're also developing your own solver, it did not fit the needs, or?
No, not exactly. I mean, so I think you're referring to Nitro especially. So first thing to know is, well, we have some strong partnership for years with Express and with FICO, because from the very beginning of the company, we have identified that having a strong partner with respect to linear and mixed integer optimization was important for us. I wouldn't pretend that Nitro is as good as Express to deal with mixed integer problems. If I did that, I would be lying. Although it's very good, it's not. it's not as good really. And especially when it comes to nonlinear versus linear optimizations, there are thousands of things you can do on linear optimizations that you can't do for linear. So you can form the dual, you can do lots of pre-solve that you can't do otherwise. You know the structure of your problem, so you can do some factorization once, so you can scale your problem once and for all. So really there's thousands of things you're doing, and that's why the big three are so great today actually. It's because they are doing all of those of this stuff, and it will take time until it gets back to other solvers. So in the end, FICO Express is very reliable to deal with a large panel of problems. It also has good defaults and good I'd say adaptation to the problem. So the defaults that change some depending on some aspects of your problem, and so out of the box, I'd say it works well. Of course, there's a lot of fine-tuning involved, so we don't use the default everywhere. But what's important is that it's very reliable, and so it's one of the main building blocks. And we know that we can throw a problem with 500,000 bits at it, and we're going to get at least one solution within the time. But just so you know, we're not putting all eggs in the same basket, and we also have implemented some heuristics, because as I said, it has to work as a solution, and you never know whether a program is 100% safe. Actually, you know that no program is 100% safe. That just doesn't exist. So someday, Express will crash. So it's just a matter of time until this happens, and until this happens, we will restart. So we have also some heuristics that are here to build some solution just in case this happens. And so we have these fallbacks, and also in case the solution returned by the solver is not good enough, then we can get another one that's computed otherwise. So yeah, when you get to operational stuff, you need several layers of redundancy. So you need servers redundancy, geographical redundancy, but you also need software redundancy.
Thank you.
Thank you. Any more questions from the room?
I think not.
Maybe,
No.
maybe another one. So you say a good practitioner needs to know how to validate algorithms. So how do you validate algorithms?
Well,
So what is strategy?
so there are many things to do. So first, there's, let's say, the methodological aspect. So you need to make sure that you're dealing with the right problem, and that your algorithm is correct. So sometimes that involves writing proof as well. So it's not because we are doing software that we don't care about the math. It just doesn't have the same visibility. And typically, I mentioned the heuristic. We have the proof of some papers that circulate internally that the heuristic have some properties that guarantees that they are optimal actually in some cases. So there's the mathematical aspect, like writing the mathematical proof. There's also the, let's say, what I call the methodological aspect, which is that you need to confront the algorithm versus the requirements. So someone, actually preferably which is external or some level of the project, need to look at the requirement, at the proposed solution, and confirm, let's say, that they match, and possibly investigate actually. Ask you, okay, why you are doing here that and here there? Are you sure this matches this requirement, and so on and so forth? And then there's of course the software validation that comes, and that also has multiple layers. So first, and they are the very obvious unit tests, so I'm not going to say anything else about that. That's something you must do when you're doing software. But there are also all of the functional and behavioral tests. So typically, when you have some requirements, you make some larger test cases that matches those requirements, and you try also to do some edge cases. So basically, once you devise a solution, then you need to think about how to break it. So you try to make the cases that makes it that it doesn't work, typically by taking the requirements to their limits. Whether it's the limits in terms of what you can imagine easily in terms of volumetrics and things like that, but also it's in many, I'd say, pathological situations, especially on markets. You have to think about what happens when you have some particular input that are unexpected. And so you design test cases to validate actually those cases, and you discuss the results with the client. Before you run those cases, you say, okay, here in this pathological case, I expect to get this result because of this requirement, this one and this one. And so you make a bunch of such cases and you validate the behavior with the client. The last category of test is a behavioral test. It's basically running the solution in exceptional circumstances, like this one typically is connected to a message broker, so I run it and then I break the message broker and I see what happens. So this is more manual test when you need to write down some procedure and do some manual action to carry out this test. Not something you're doing every time, but once in a while it's necessary.
Thanks. We should give a chance to the audience. Any questions from the online audience? If yes, just please unmute yourself or use the chat if you are shy.
Hello, I'm not shy.
Oh,
Thank you, Michael, for a nice talk. I would be really curious. Computational power is obviously improving, same as the algorithm, year after year. So the problems, like the real-time problem, probably would not be solvable to the same limit if we go, let's say, back 5 years in time. So what happened actually in the past? Were the problems significantly easier, or were basically the systems satisfied with lesser quality solutions? And second question, what do you think happens in the future? Will it get even harder by connecting more people and, I don't know, renewals and I don't know what else? What do you think? Thanks.
Okay, so typically in the past, this solution, the one that I last discussed, the TER solution, it's not something that was imaginable actually 5 years ago. There was some, for instance, there was something else that was in place, but we were just lacking a few things. So we were lacking the regulation first, so it's not a very funny thing, but that's true. And we were lacking as well, let's say, the capabilities, the technical capabilities to do such things. Designing such a system today with so many interconnecting TSO, it was doable 5 years ago, but maybe for 10 times the cost. So that made it unreasonable. But nowadays, especially thanks to well, a bunch of techniques, including first our experience, our global, worldwide, I'd say, experience in optimization. The solvers are more and more robust. The hardware also is more and more reliable. You had a strong development of cloud infrastructure as well, so that made it possible to have geographical redundancy, for instance. So you have also microservices and things like that. That was not as trendy 5 years from now ago. Sorry. So of course the technical development, like the world changed basically in computer science in the last decade, even the last 5 years. So there's been a huge gap there, which is, in my opinion, this, let's say, software gap is really what matters, because in terms of hardware 5 years ago, we knew how to do HPC, for instance, but cloud was not as popular as it is today. What will it be 5 years from now? That's a difficult question, of course. I think we'll have even more reliable solution in terms of optimization. Hopefully, we'll be able to have a larger panel of techniques which are available. As I'm developing Nitro, I'm hoping that 5 years from now, we're going to have a nonlinear optimization solver that works out of the box. That's still well, you still need to be an expert to, truth be told, to use nonlinear optimization these days, unless your problem is quite simple. It's good for you to know a few things. So making those techniques reliable and hopefully polynomial optimization as well in a few years from now, that's the scientific goal that we can have. And in terms of computer science and hardware, you can see that things are quickly moving with orchestration and things like that. So I expect it will be even more easier to deploy and manage very complex solutions with thousands of services than it is today. So that's, I say, my expectation.
Thank you.
Okay, thank you. So we are quite over time. I think we should finish this session. Thank you very much again, Michaël. I'd like to ask Bernard if we start the next session on time in 15 minutes or later.